Okay. Again, going back to, we're going to start again with the circular motion, or circular acceleration equation. If we want to figure out the period and frequency given an amplitude and acceleration, this is the equation that we're going to use. Here's where we're going to start. Okay, again, start with that, know the equation that you guys know. And we're going to sub in.
No.
Oh no, we don't want to make this work. And sorry, give me a second. That's right, we leave it. Okay. No N. Just sub in A for R first. And now we're going to rearrange it for frequency. So, F squared is equal to A divided by 4 pi squared capital A. And if I square root both sides, the 1 over 4 pi squared, I'm going to pull out of the radical to just leave it as 2 pi. But the root acceleration over amplitude, I'm going to leave under the square root. So this equation is to give the frequency or period, we're going to flip everything when we get period here, of an object undergoing simple harmonic motion. Here's the thing. I can't. The problem with the you guys saying in your heads, well, can we do an example, please, at this point? Why does all this come in? Most of the examples kind of go like all over the place. So I need to give you guys at least a foundation for equations before we can do some examples. But I promise we will get some examples. So that projection of a circle, it can be used to think about simple harmonic motion, and it can be used to derive the first equations, but it's not actual simple harmonic motion because the force, we're in two dimensions for the actual circle, so the force is actually, it's a constant force in 2 dimensions. The simplest actual simple harmonic system that we look at is a horizontal spring mass system. So I'm going to show you what that looks like and how it's exactly the same thing. Yeah, I want to run the application. All right. So you can see how the projection of that mass on a spring, assuming there's no friction and no loss of energy, it'll keep going forever. and it'll keep projecting that, creating that sinusoidal path. Okay. So the equilibrium point would be right in the middle, right about here. Okay, and the force is always pulling it back to the equilibrium. Okay. And that's the important part about this harmonic motion. So the next set of few equations are going to be specialized. We're going to take those general equations that we just did, and we're going to specialize them for a spring mass system. No, actually, it's wrong.
With the free. Oh, yes, I can see it.
Oh, but before we get into the equations, we do some graphing here for a second. Okay. Oh, what happened to my? Your graphs printed out fine, didn't they? Oh, mine did not. The conversion from the Word file to the Smartboard file did not work too well here. I'll have to use the Word file.
What's going on?
Yeah, okay. Just hopefully the ink works. Sorry, technical problems. Okay, so we pull the spring to its maximum extension and let it go. And we see that the period is 0.4 seconds here. This is 1/10 of a second. So there's one complete cycle of the object's displacement from equilibrium. And we can do 2 cycles here. Whoa, stay there. Yeah, because I said the period is 0.4 seconds. So it's, yeah. And X is in centimeters. Now this is the only time all year I'm going to say this to you, but the proof for this formula I'm going to show you is too advanced. Okay, it requires like second year calculus.
You will probably can explain it.
Oh, I know it. I can explain it, but I'm not going to. It requires the solution of a what's it called? A second order homogeneous differential equation. It's a little complicated. What's that? Sure. It's kind of neat. So anyways, you don't need to know that proof. It's not in the grade 11 IB physics curriculum. So I'm just going to end up giving you the equation here. X equals... Oh, what's the problem here?